Okay, let's talk about Carnot cycle. So what have we doing so far? We are trying to prove that entropy is a state function for any gas, any material, any cycle. So recall what we are trying to do is that, for example, in a pressure volume plot, but this could be pressure temperature, this could be anything. If you start from a point, you come back over here, then the entropy along this path, delta S path or delta S along this cycle is going to be 0 for any gas. This is any substance. This is what we are trying to prove. So in order to do this, our step 1 was to look at a very special cycle, which we called the Carnot cycle, right? We had, which one was, this was the isotherm. We had an adiabat, we had another isotherm, we had another adiabat. So iso, adia, iso, adia. And this one was at a hot temperature TH. And this one was a cold temperature TC. And this one was taking in heat QH. And this one was giving out heat, but we call it that it was taking in heat QC, which was negative, right? So we showed that indeed for this process, for an ideal gas, if you go from 1 to 2 to 3 to 4, we show that delta S Carnot ideal is equal to 0. Remember, in order to show this, we calculated, I numbered the points here, which might be confusing if you refer to last time, but we calculated that basically this is going to be the term sum of the two isothermal processes, delta S iso hot, delta S iso cold, right? Because adiabatic process has delta S is equal to 0. We don't have any doubts about it. And we calculated this. And does anyone remember what this came out to be, the delta S net? Go ahead. Yeah, but what was the expression? You're right, it came out to be smart guy. You can look at, don't even look at your notes, just look at the figure and tell me, JP. Even simpler. It's an isothermal process. Yeah, go ahead. QH by TH plus QC by TC, right? I think Hannah answered it, right? We are integrating and we can just take the temperature out. That was the idea. Good. Yeah, I like to ask questions. It keeps everyone awake. Of course, every time in the course evaluation, 2 or 3 students call it traumatic. And I'm sorry, it's kind of mean of me to ask you questions at 9 a.m. But what's the point, right? If you're just gonna come here and sleep, don't sleep. So, and we showed that this is indeed equal to 0. Now, before we go to the next step, it's a bit abstract. So let's look at this Carnot cycle from a slightly more abstract perspective. You can think of this Carnot cycle as something that is taking in heat from a reservoir at hot temperature TH, taking in some heat QH, and dumping some heat to a reservoir at a cold sink. So this is not one thing I should be clear. Normally, both of these are reservoir. By reservoir, I mean you are taking in heat from a much bigger source, which does not care whether you are taking heat out of it or whether you are dumping heat into it, right? It's the surrounding. When you are taking heat out of something, we tend to call it a source. When you're dumping heat into something, we tend to call it a sink. For this class, you can just call both of them as reservoirs. It's okay. We won't get too much into source and sink, but that's the idea over here. And through this, you could imagine that maybe you're able to do some work out of this and drive a process, right? Why should we be able to get some work out of the Carnot cycle that I drew above? This, it's not a square, it's not a rectangle. The shape, what should I call it? Quadrilateral. This quadrilateral, right, that I drew above. During the whole quadrilateral, should it be possible to get work out of the process? Go ahead. Yeah. Yeah. In fact, if you think about it, delta U is equal to delta Q plus delta W, right? What is delta U when we go around all the way and come back? 0, we all agree, right? What is delta Q? Is delta Q 0? No, because QH is not QC, right? QH is different from QC, most likely. Most likely QC, we know QC cannot exceed QH. You cannot take heat and dump more heat outside. If it's efficient, if it's reversible process, we know QC becomes, we know QC is going to be smaller than QH. So we know delta Q is not 0. So therefore, delta W also must be not 0. So we are able to get some work out of it, right? So we can define an efficiency for this process, which we introduced last time. The efficiency is defined as the work that you get out of this process divided by the heat that you had to suck in order to do this process. So W by QH. And we know work is going to be QH minus QC. It is the difference of both of the heats. You can see, just see from this formula, right? Since the whole thing is 0, therefore work is going to be delta W is going to be minus delta Q. And this has nothing to do with ideal or non-ideal, right? This could apply to any gas, right? Because U is a state function for anything. Go ahead. I haven't said anything about what this value will be. Okay, I'm just writing down something very general. So this is QH minus QC. So this is 1 minus QC by QH. This is true for anything. Any substance operating along a Carnot cycle will give you this efficiency. What we showed last time is that QH by TH plus QC by TC is equal to 0. Let me write it down here. It's so important. QH by TH plus QC by TC is equal to 0. Right? Remember this expression and look at this expression for efficiency. Let's call this equation number 1. So Carnot cycle efficiency for any gas is equal to 1 minus QC by QH. And if you look at this expression, QC divided by QH is equal to TC divided by TH. This is true only for an ideal gas, right? This is not true. In general, this is true only for an ideal gas. For ideal gas, eta Carnot is equal to 1 minus TC by TH. So the claim now, and I'm going to make a very, very big claim. I'm going to make a claim that if you had a hot source and a cold sink, right? The process that I drew over here is one very specific process where you did an isotherm and an adiabat and an isotherm and adiabat. So the claim now is given hot source at TH and cold sink at TC, Carnot efficiency is the highest efficiency possible for any reversible engine operating between those two temperatures. This is a bold claim. I'm telling you that if you had this picture, once again, PV, and you had some point here, and you had some point here, and if you want to suck in heat from a hot source at a temperature TC, and you want to dump heat to a cold sink at a temperature TC, you cannot possibly construct any other path by doing blah, 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 whatever you want, which will exceed the Carnot efficiency. That is the maximum efficiency you can get if you are operating between a hot source at TH and a cold sink at TC, and you're taking some QH out and you're dumping some QC here, and you're using this to drive an engine to get some work out, you cannot exceed the Carnot efficiency. A corollary, an equivalent statement to this is, sounds even more absurd, the next one that I'm going to write. All engines, i.e. all substances, real or ideal, operating reversibly. Let me just stay with the first one. This will confuse. We'll come back to this later. So this claim, sorry about that. This claim that I just wrote, it's important. It actually has a name. It's called Carnot's theorem. That the Carnot efficiency is the highest efficiency that you can attain between a hot source and a cold sink. It was proved by Sadi Carnot, who I believe was French. I checked on Wikipedia, but I forgot. And he proved this in around early 1800s or something like that. So we have to prove this. Why do we want to prove this? Because if we prove this, why do we want to prove this? Any idea? Why should I waste your time proving this? Is it clear to anyone yet, or is it also confusing? Go ahead.
If you can prove this, then it's applicable to any path. Any path would have like more sort of.
Any path comes later. It will be applicable to any substance. If we prove this, then the point that we made last time, that so the equivalent statement is actually better. So the equivalent statement to this is that all reversible heat engines have same efficiency between hot source TH and cold sink TC. If we could prove this, then this means that the efficiency expression that we derived for Carnot is applicable to any derived for Carnot for an ideal gas is applicable to any substance. Okay, so let's work through it carefully, and then it will become clear. So let's imagine that there is, let's say this is not true. Let's say it is possible to have two different engines, both of which are operating between a hot source TH and a cold sink TC. And they are operating reversibly. What does reversibly mean? I can flip the direction, right? And it will still work. They are operating reversibly. And one of them has higher efficiency than the other one. Let's look at this scenario. Let's imagine that there are two engines, reversible, with different efficiency. And we will show that this leads to a contradiction. This violates the second law of thermodynamics. So let's work through this with different efficiencies. So we have a hot source at TH, and we have a cold sink at TC, and we are taking some heat QH out, which is positive. We are using it to turn a motor and get some work out of this process. And in this, we are dumping some heat QC. So let's say that there is an engine A that does something like this. For engine A, let's call it needs to take heat QHA and dump heat QCA. Okay, I have applied superscripts. Now let's imagine there is another engine B, which is also operating between the same temperatures, hot source TH and cold sink TC. This one is, however, taking heat QHB out of it. It is dumping heat QHC, which is going to be negative because it is loss, and it is getting some work too. So, and I'm claiming that it is possible that the efficiency of engine A is more than the efficiency of engine B. Okay, what is the definition of efficiency in terms of heat? It is 1 minus, if you look over here, the proof, this is only for ideal, right? We haven't proved this for anything else yet. That's what we are trying to prove. But we do know this is true for anything. Eta is equal to 1 minus QC by QH. So 1 minus QCA by QHA is more than 1 minus QCB by Q hot B. Okay, or QCB by Q cold B by Q hot B, we can bring it to the right, this can come to the right side, is more than Q cold A by Q hot A. Okay, this is fine. Now let's make an assumption that let's keep the heat sucked out, the heat dissipated to the cold part the same. Okay, let's keep QCA is equal to QCB. Let's say both of these engines are dumping the same heat into the cold sink. You might say, I don't like this. Why are you doing that? You could do the same thing by not saying that, but by keeping the same heat coming out of the hot source. There are so many parameters right now. We want to fix one of them. So we fix this one. Let's take a step back away from the equations and look at what's going on over here. So who here thinks they are like a very fast sprinter? Who here has run a mile under 5 minutes? You have run a mile under 5 minutes? That's really, really fast. Okay, my best mile is like low 6 minutes. So remind me your name again? Daniel, sorry, I keep forgetting. So Daniel is very efficient, right? Daniel and I go for a run. And we both are, when we are running, what is the equivalent of a cold sink? Where are we dumping heat? Sweat, right, into the atmosphere. So we are both, let's say, sweating at the same rate. But Daniel is more efficient, clearly, because he can eat a bagel and go run 5 miles. Sorry, a minute at a 5 mile pace. What's your PR in a mile? 4:58. He's really fast. Okay, so 4:58. Last year I had a 4:15 in the class, by the way. We'll talk about running later. So he's very efficient. So Daniel and I both are dissipating heat into the atmosphere, right? That is our cold sink through sweating. So what we are saying is the amount of heat we are losing through sweating, let's keep it the same. It's an approximation. But now that Daniel is more efficient than me, what does it say about W Daniel versus W Pratyush? Which one should be higher? W Daniel, right? He's being able to get more work done out of it. What does it say about QH Daniel versus QH Pratyush if QCs are the same for both? QH Daniel should be higher, right? He's able to suck out more heat out of the cold. So maybe this gave you intuition, maybe it gave Daniel intuition, maybe it gives someone else intuition. But so the idea here is that we can keep the cold sink as the same. Now let's see what it means about everything else. So if we keep QCA equal to QCB, now I will mathematically prove what I just said, that this means that Daniel must be taking more heat out of the, let's see what it means mathematically, because we have also talked about efficiency, right? So we have to keep that thing in account. So this means if QCA is equal to QCB, so this thing in the numerator can be canceled out, right? This is the same both sides. Therefore, QHA, this thing comes to the numerator over here, and QHB, this thing goes to the numerator on the other side. QH, I know it's a lot of subscripts. Let's work through this. The good thing is Atkins also goes through this, and videos and notes will be online. So if this is confusing, please go through Atkins. Please look at this again, because this is important. So QHA must be more than QHB. So what have we shown here? We have shown that if, recap of this one, if A is more efficient than B, and A and B dissipate same heat, then A must be sucking in more heat from hot source than B. This is not exactly obvious, right? Because if you think about it, you might have said, well, why does Daniel have to take more heat out? Maybe he's just so efficient that he's just taking the same amount of heat, but that's not going to happen, right? Because first law of thermodynamics stops us, delta U is equal to 0. So there is no other way. This is what we have. What do we do with this? We can do something interesting now. So let's call which one. A is more efficient, right? So this is Daniel, and this is Pratyush. I think Daniel and Pratyush are a bit better than A and B, right? Let's draw their photographs. This is Daniel. He has hair, not too long. And this is me. I have a bigger smile though. Okay. So we are both dumping heat for anyone who came late and you're looking at this, you're like, what on earth is going on? Just head back out. It's not that bad. Stay with me. It's something intuitive, and look at the notes later. So the important thing now is that both engines are operating reversibly. Okay, so let me draw this on the next page and we will proceed from here. What we have so far. So we have Daniel, or engine A, for those of you who do not like names. This one is operating from a hot source, taking some heat QHA, doing some work out, and dumping some heat to a cold sink at TC. It's important to keep drawing it, otherwise I think it will help understand if we draw it a few times again and again, the same thing. And it is dumping some cold heat to the cold sink QC. And I'm not going to write QCA or QCB, right? Because I'm forcing both of them to be the same. And over here, I had engine B, which was also operating between the same hot TH, taking some other heat QHB, doing some work W, and notice I haven't compared Ws yet. We will do that just in a moment, and dumping some heat QC. So, and both of these engines are operating reversibly. We are not interested in irreversible processes right now. We will talk about them, but we know that irreversible processes tend to have lower efficiency anyway, so we don't care about them. We are just talking about efficient processes. So they are reversible processes, and both in the bottom part have the same heat. So we can do something interesting. What we can do is to take process B, and since it's reversible, we can run it in the opposite direction, right? What we can do is to imagine, and I will draw it, and this is the part that is the most simple yet kind of abstract. So I'm going to draw it in red, okay? We will run, so it's like I'm converting sweat into food. I mean, that's the thing that's going on over here, okay? And we will lead to a contradiction. So this one, I'm going to take heat out QC from the cold source, and I'm going to dump some heat into TH, and I can do it reversibly. So I will have to worry about signs, but the magnitudes are going to be the same, QHP. Can I do this on its own? What does one of the statements of the second law of thermodynamics tell me? Go ahead. Yeah, what does it say? Without doing any work, I will have to do some work. If I do some work, then I can pull heat from a cold sink and dissipate it into a hot source. That's how air heaters work, right? They are taking some heat from the outside cold atmosphere and giving it back to you. So I will need to do some work in order to do this process. I won't be able to get work out of it, right? If you want me to be someone who takes energy from sweat and consumes it into food, I'm not going to be running. No, it's going to be something opposite, right? I won't be doing work. You will be doing work on me. So notice the sign of the direction of this W, I have brought it backwards. Now let's talk about WA and WB, and let's look at it carefully. Okay, so again, this is very different from the type of arguments we have been making, right? It's kind of math, kind of intuitive, and it's confusing. So just to recap, so far we have said we have two engines, A and B. A is more efficient. Eta A is more efficient than eta B, or 1 minus QC by QH for A is more than 1 minus QC by QH for B. And we said, okay, let's keep QC is the same for both, same amount of heat being sunk in. This led us to prove that this implies if QCA is equal to QCB, then this implies that QHA is more than QHB. And now so this is one thing I proved. After that, I made a thought experiment. I said that, okay, let's run the second engine, which is the less efficient engine, has to be run reversibly, okay, in the opposite direction. It is taking some heat out of the cold sink. Now I have to do some work on it, and then it dissipates some heat into the hot source. Go ahead. Let's go back over here. So no, I don't think so, because in this expression, this comes to the left side, right? QCB by QHB is more than QCA by QHA. QHA is more than QHB. Did I make a mistake here? No, you think about the minus sign. So let me write it down over here. Yeah, it's minus. Minus is everyone's nemesis. Minus is terrible. Okay, let's focus on this. So yeah, but if anything confuses, please ask me, okay? Because I make lots of mistakes. So QHA is more than QHB. So that was first part of the thought experiment, that we run it reversibly. Now let's go to the second part of the thought experiment. So we run it in the opposite direction. So the first experiment, run B opposite. Run B in opposite direction. Now we can do something else. We recognize that, well, think about it. They are both operating between the same hot source and the same cold sink, right? So instead of thinking of them as two separate engines, let's look at them together. Together, what are they doing as one engine, right? So let's draw a big hot source over here and a big cold sink. This is TH and this is TC. So this one is taking some heat out QHA. This one is giving some heat back QHB. A is doing some work, WA, and B needs some work to be done on it, WB. How much heat net are we giving to the cold source? After looking at both processes together, what is the net heat being lost to the cold sink? Sorry. I heard a number, nice number, 0. Why? Are the same, right? So A is dumping QC into the cold sink, and B is taking QC out of the cold sink. So together, 0 heat lost. Now we are starting to get to something. If we could show that this process, you are actually able to get net work out of this process, then we would have a problem, right? Does anyone see why we would have a problem? You already answered. Someone else? Go ahead.
infinite free energy.
It will be what?
Plug it back into itself.
Well, it is in violation of Kelvin's statement, right? You are doing a process where the net effect is you're taking some heat out of a hot source and doing it to do using it to do some work. So let's look at now WA and WB. So what can we say about WA and WB? We have efficiency eta A more than efficiency eta B. We have QCA is equal to QCB. We have QHA more than QHB. Therefore, we have WA more than WB. So the work that you are getting out of the process A is more than the work you need to drive the process B. Daniel is so efficient in running that he's basically, I can run myself in opposite direction, and net process would look something like this. Hot source, TH, cold sink, TC. You are absorbing heat, QHA minus QHB, and you are doing work, WA minus WB, and no heat lost to cold sink. And this is in violation of our Kelvin statement. This is not possible. Kelvin's statement of second law of thermodynamics says you cannot have a process where all you are doing is to take heat out of a hot source and converting it into work. If we had such a process, its efficiency would be 100%, right? There is no heat being lost. So through this abstract argument, we have just shown that our original premise that we can construct two engines, reversible engines with different efficiencies, has a problem. We cannot do that. If we had two engines with different efficiencies, we could run the higher efficiency engine in the forward direction, and we could run the backward efficiency engine, the lower efficiency engine in the backward direction. And net effect would be a process where you're not losing any heat to the sink and you're converting everything into work. And that would be in violation. So this proof is abstract. After this, every year, some students ask me, what do I do with this proof? I'm going to forget this. Are you going to grill me on this in the exam? I won't be asking you to, in an in-class exam, I want you to understand this and use this and remember this. This proof is abstract, it's complicated. We could not have just thought how to do this on our own, but you need to remember the main message out of this proof is all reversible engines acting between hot source TH and cold sink TC have same efficiency. Therefore, delta S Carnot for any gas is equal to 0. And it's not just they have the same efficiency. We also got an expression for that efficiency. And that's the thing that you need to remember. What is the expression for that efficiency? Huh? 1 minus TC by TH, right? We could always write down the efficiency in terms of the heat, QC by QH, but QC depends on how the process is being operated. Any questions? Is really no one falling asleep for this? This is kind of boring, this stuff. It gets very abstract. Okay. We have not yet proved that any cycle, irrespective of hot source and cold sink, any cycle in a space, in a PV space, will give us delta S equal to 0, right? That's the final step that remains. This final step is also slightly abstract, but as not as complicated as what we went through. This proof that we just finished is possibly one of the most abstract things in the whole semester. There will be many things which are slightly less abstract than this, but I don't think we will get more abstract than this one. It's also, it comes early on, so it's a bit complicated. But please go through this. This proof is abstract, but it's not too hard. But not too hard. Please read it again. And Atkins also has the same proof. So please go through it again. Please try to understand it as best as you can. And remember the fact that all engines acting between hot source TH and sink TC, all reversible engines must have the same efficiency, 1 minus TC by TH. Okay, and this is why this Carnot cycle is an important cycle. It looks abstract, but it leads to such an important conclusion. Now we have to do the final part of the proof to prove that. So this is the final third part. To prove that delta S cycle is 0 for any cycle and any gas. So by the way, one type of problem that especially you can get in like multiple choice type exams, MCAT or whatever, you can be asked to calculate the efficiency for a heat engine acting reversibly between some temperature 400 Kelvin and 500 Kelvin. For that, you don't need to know all this proof, right? But if you remember the gist of this proof, the end of the proof, the expression for the efficiency, you know how to calculate it, right? So given the temperature, you can calculate the efficiency. But now let's go to this final part. So here we want to prove that let's draw a big pressure volume diagram. Any cycle, I start at a point, some P1, V1, T1, and I don't have any concept of a hot source or a cold sink, nothing isothermal, whatever. Any cycle that I have here, something that goes like this, for any gas, delta S, any cycle, any gas is equal to 0. That's what we are going to do now. How do we do this? The idea here is to think of something like this. You know how the shirt is made up of little patches? To take this complicated cycle and imagine little Carnot cycles inside it. So let's go to this point over here and we draw one Carnot cycle that looks like this, another Carnot, a second Carnot cycle that looks like this, and just cover it with, if it will take me a lot of time if I try to cover the whole thing, but you get my point, right? Just cover it with Carnot cycles everywhere. Cover with tiny Carnot cycles everywhere. Okay. If you do this, then let's go and look at these two random Carnot cycles right in the middle, Carnot cycle A and Carnot cycle B. Okay. So Carnot cycle A operates like this. The arrows matter for this one. Carnot cycle B operates like this. Down below this Carnot cycle, I'm going to have another Carnot cycle. Call it Carnot cycle C, which operates like this. And over here, I will have another Carnot cycle D that operates like this. If I want to calculate delta S plus A plus delta S B plus delta S C plus delta S D, if all four of these were Carnot cycles, what could I say about the value of delta S A? Forget about this big patchwork. I'm just asking you, Carnot cycle if delta S along a, yeah, go ahead. Zero, we just proved this, right? And it doesn't have to be an ideal gas. Any gas, Carnot cycle, delta S will be zero. We just proved this. This is zero, this is zero, this is zero, this is zero. So we know that delta S A plus delta S B plus delta S C plus delta S D is equal to zero, right? It just, this was part 2 of proof. But if you look at this thing carefully, you will realize that delta S A plus delta S B is also the same, and I'm going to run out of colors. Let's use pink. Is the same as only looking at the pink part. Why? Because the parts in the middle cancel out, right? A is working in some direction and B is going in the opposite direction. So even if there is path dependence along this part, it's going to cancel out because A covers it along middle, contributions cancel from A and B. Makes sense? Atkins has a nice, beautiful picture of this. I cannot draw that well ever in my life. That's definitely not on an iPad. Please look at it. That said, if you did not attend the class and just looked at the Atkins picture, I'm ready to bet you will still be very confused. So it's the combination that is really useful. So we have these 4 Carnot cycles, and the path in the middle cancels out. Over here also, it cancels out. It's coming from 2 different processes. So we have just shown something interesting. We have shown that this sum is equal to delta S perimeter, right? You could just go along the perimeter of this thing. In the direction is important, in this direction. And what would thus be delta S perimeter? 0, right? Because they are the same. I just showed it to you here for 4 Carnot cycles. You can imagine the whole thing can be done for all Carnot cycles, right? In the whole system. When you keep drawing things here, the only things that will matter is the ones at the edge. Everything else in the middle will cancel out. The things at the edge will matter. Therefore, delta S any cycle is equal to sum of delta S tiny Carnots. That's the whole idea of this proof, right? You have a big complicated thing, you decompose it into little patches, and you realize that all the ones in the middle cancel out. You're only left with the contributions from the edges, like I showed you over here for these 4. And we know that tiny Carnots or big Carnots all have efficiency 0. So you're summing over a bunch of processes, all have delta S0. So you're summing over a bunch of processes with delta S0. Therefore, the full thing is 0. And that completes our proof that entropy indeed is a state function. Hooray. If you forget all the details of this proof, that's okay. Remember the gist. How did we do this? We constructed a PV diagram for a Carnot cycle. We showed that the efficiency for an ideal gas for a Carnot cycle is 0. Then we said, well, turns out this is not true just for an ideal gas. This is true for any gas operating between TH and TC reversibly. They must have the same efficiency. And finally, we showed, well, this is actually not true for Carnot. This is true for any cycle. So our entropy indeed is a state function. Next time, we will go to something called Clausius inequality. we will start to gradually get into irreversible processes now and see what is the difference.